guys don't mind me perusing very, very quickly to what I was referring to as those other properties of determinants. Oh, come on, you can't be that slow. You're a brand new computer. I maintain, even if I go so far like I did with augmented matrices, replacing one row of a determinant with k times another row added to it, then I think it's not going to change the evaluation of my determinant. And so what I want to do next is look at those few properties of determinants. Boy, I am really in the black.
There you go.
Okay, guys, can you hold on a second, because this particular camera is a little different. I have to autofocus, so hold on a second. I don't want to make you sick. All right, here I go. Autofocus. So I have a variety of determinant properties. I've already, in a sense, walked through the proofs of the first two. I just mentioned the third one. I'll leave this for you to read. Want to transpose a matrix? Determine either one, the original one, or its transpose. It's going to be the same. This one is a special case, just looking at columns, or rows in this case. Which ones am I missing? Actually, I walked myself through the proof of the 6 and 9. Oh, here is something I did miss. Actually, I can walk myself through the proof of this one real quick. If the rows of a matrix A are interchangeable, or even the columns, I think what this one's going to do is basically, oh, check this out. It's going to be taking one times another row, adding to itself. That's going to force one of those two rows to be zeros, and that just defaults me back to the property number 6. So I'm hoping now that today I got to that formal definition of a determinant, you guys can take a peek at these particular properties and say, yeah, that's got to be the case. Actually, maybe that means I can exploit these properties. So you guys, if I were to evaluate this determinant, actually, can we do it from scratch, no tricks, just to see if I get a number that's meaningful? And so no tricks. Expanding about, how about the first row? It's easy. Expanding about the first row. Wouldn't I just get this 2 by 2 right here? 6. Say it again. 7. I like 7 better than 6. I'm going to add that to the determinant I get right here. Wouldn't that just be a 3? Oh, but times that position, which would give me a 6. And I think that's going to give me a 13. But let me show you an alternative. What if I came in, took this determinant, 1, 0, 2. What if I multiply the first row by -3, added the second? Wouldn't that give me this? Now if I came in and say multiply, whoops, it's not a matrix, it's a determinant. Multiply the second row by a quarter and added it to the third row. Wouldn't that give me 1, 0, 2? Is that a 0, 4, -5? But I said multiply the second row by 1/4. Actually, I misspoke. Multiply the second row by -1/4, add it to the third row. Wouldn't that give me this? 0, 0, oy, oy, oy. I'm starting so slow. So -5/4 plus 8/4, is that 3/4? You guys, is that correct? Yes, Michael.
I'm confused on the first example. Where does this 5/4 plus 8/4?
I don't know, double check my arithmetic. Remember, I was listening to cofactor expansion of the first row. And so I was multiplying 2 by this dotted 2 by 2.
Oh, yes.
Oh,
Wouldn't that give me 2 times the quantity 6 minus, excuse me, 2 times the quantity 3 minus 0, which is really my 6.
I think the bottom needs to be 13 over 4, because it's negative 1/4 times negative 5 plus. So
My
5,
apologies, I agree completely. You said 18 quarters.
13.
13 quarters. Because I get a positive 5 quarters plus 8 quarters is a total of 13 quarters, I agree. By the way, what does this turn out to be?
13.
Oh shoot, look at that. Get the same answer. So sometimes I might want to row reduce, maybe not completely, but row reduce to get an upper or lower triangular matrix. And if I do, I can evaluate the determinant very quickly and easily. That was the point of my redoing it. Make sure you got the same answer we did before. So if you're interested, this is truly something. So you guys, I need to come back to something else. I need to come back to how you and I actually listed the cofactor expansion technique for evaluating determinants. So can I go back? Do you remember how you and I said we could listen this way? You guys are all my symbols correct?
Yep.
I'm not trying to trick you, I assume they are. I meant them to be. But you know, there's a different way to quantify these expressions in here. I might think of the first one as A11 times, can I change my language? How about saying it's A11 times, well, taking A11's position, eliminating its row and column, I'll consider this the minor corresponding to A sub 1, 1. Minus A sub 1, 2 times. Well, likewise, I'll think of this determinant as attained by removing A12's row and column as a minor corresponding to first row, second column. Plus, my A sub 1, 3 times, well, here too the minor corresponding to row 1, column 3. Or how about if I say this? I got A11 times 1 times M11 plus A sub 1, 2 times negative 1 times M sub 1, 2. And finally, A sub 1, 3 times positive 1 times M sub 1, 3. I got a new definition. I will consider 1 times M11 the cofactor corresponding to the entry in the first row, first column. Plus A sub 1, 2 times the cofactor corresponding to 1, 2's position. And finally, A13 times C13. I will think of the C sub ij as cofactors with this expansion. It's just simply nothing more than the minor corresponding to nothing more than the positive negative sign of these individuals. And I maintain the cofactor expansion associated with the ith row jth column is nothing more than negative 1 raised to the sum of those two positions. This is why yesterday in class I was saying to determine the sign of these particular smaller determinants. You simply add together the row position to column position raised negative 1 to that power times the corresponding minor for the same row column position. That's my definition of a cofactor. And by the way, I guess this finally formalizes how I'm actually going to define this cofactor expansion technique. It's merely the alternative technique for evaluating a 3 by 3 or any size and by n determinant.
Can you just quickly explain, I think I lost you a little bit here, just from step 2 to step 3 there for you.
You mean from here to here?
No, I got that.
Then this is the easy thing.
Where you swapped it out for the C. Yeah.
I was simply saying, can I just bring in whether or not I don't or do get a sign change?
I got that.
And I associate it from the end. And then I simply said this. These circle beasts
Okay.
are what I'm referring to as my C sub ij's.
Okay.
Nothing more. And how do you determine whether or not you get a sign change with the minor? You just simply add together your row position, column position, raise negative 1 to that power.
Okay.
Here's something else you can put in your back pocket.
Is all this stuff in the book as well?
Absolutely, yes.
Okay.
Is there anybody in this room who happens to have that example that I keep looking at in class? Nobody has it? Yeah, actually the one I've been doing for the past couple days.
The 2x minus 2y minus 4z.
Yeah.
So wait, 2x,
Minus 2y, minus 4z, equals negative 6. 2x plus y, minus z, equals negative 1 x plus y, plus 2z equals 5.
and I think one technique we use is we use the inverse matrix to come up with a solution to the system. And of course, I wrote up a single matrix equation, et cetera, et cetera. But along the way, we had to determine the inverse matrix, and I can't remember what it was. But can I show you? I wanted to get the vector spaces today. Can I show you a technique, an alternative technique for computing the inverse matrix?
Sure.
Okay, here it is. I'm going to come up with what I would refer to as a matrix of cofactors. And when it comes to the matrix of cofactors, I'm going to consider the coefficient of change. Now, I maintain that the cofactor associated with 2 is going to be nothing more than 1 times this determinant. But isn't that just going to be a 3? The next cofactor corresponding to first row, second column, that's going to be negative 1 times. Oh, I messed up already. Gosh, you guys, I really did. Did I get my signs straight? I said the cofactor associated with this is going to be this 2 by 2 and it's times positive 1. Yeah, I like it. I'm there. What about the cofactor for this one? What's that going to evaluate to?
5.
Is it?
Negative 5.
Negative 5, because the cofactor corresponds to actually the, sorry, it's slow, the position, the negative sign change. So did you say negative 5? I lost it.
Wouldn't it be
Yeah,
positive?
but would the negative 2 negate that or not?
No, because I'm only looking at the cofactor. What about the cofactor here? What would that be?
Or 1?
1. I agree. And now if I look at the cofactor expansion.
I'm just wondering how you got negative 5. Because wouldn't it be,
Well, if I take this position's row and column and eliminate it, look at the 2 by 2 determinant.
yeah, so it'd be 4 minus negative 1, which is 5.
positive 5.
But you put negative 5.
Yeah, because now I'm going to, if I look at the cofactor expansion, I multiply by negative 2 with a sign change
Oh.
on the outside. It incorporates the
Yeah.
minor and
No,
the
no, no,
sign
no,
change.
I see what you did. All right.
What about cofactor expansion here? Would that be positive or negative? Yeah, I think it'd be negative because I'm in the second row, first column. I think the sum of the row position, the column position is going to be 3. Negative 1 to 3 is going to be negative 1. I'll get a sign change, no sign change. Sign change, no sign change. Sign change, no sign change.
Okay.
Let's dive in. I'm back over here. I know I get a sign change. Let's compute the 2 by 2 I'm getting. What would it be? I think it'd be 0. So don't worry about the sign change this time. I think when it comes to this position's cofactor, it's going to be positive, so let's not worry about sign changes. But for this position's cofactor, what would it be?
8.
I agree. I got a positive 8. Next.
4.
Oh, you know what? I just did the wrong row. Hold it. So, sorry about that. I come up with negative 4. Next, down over here, I'm going to generate a... You guys don't want to play anymore.
6.
I got a positive 6. Next. See, I came with -6. Because I've got, let's see, -2 minus -8, but that's -2 plus 8. Isn't that +6? But I get a sign change. And lastly, 6, that's what I came up with. What I want you to do next is consider the transpose of that particular cofactor matrix. And if you take a peek at this transpose, it's simply going to be another 3 by 3. I'm just going to interchange columns and rows. And I maintain as an alternative technique for generating the inverse of that coefficient matrix A, I'm simply going to do the following. I'm going to come up with 1 over the determinant of that matrix A times what I'm going to now define as the adjoint of that matrix A. And when it comes to the adjoint of the matrix A, I'm simply looking at the transpose of the matrix of cofactors, nothing more. It's just an alternative way of computing the inverse matrix. And in this particular example, I think I get a fraction times that adjoint, which I've already computed as 3, 0, 6, -5, 8, -6, 1, -4, 6. Hold on, you guys, I'm in trouble. Let me turn on the screen. And if I were to compute the determinant, I got an idea. We'll cheat. Can I erase this?
Yeah.
Wow, that's getting hot.
You should consider changing your password. It's going to expire.
I can't. Every time I get a MySierra including today, the system's backing up.
Oh, really?
And won't be changing it. We have about 1 day left. So if I can't get into my account, we'll just cancel class for the rest of the week.
Okay.
Yes, I know a class, and I know it's messed up. You guys, I'm just cheating. I want to do all the extra work, and you don't want to sit here and redo all the arithmetic. I'm going to skim down to when I use Cramer's rule, and I'm going to identify what the determinant of the coefficient matrix was. There it is, positive 12. So do you guys mind if I cheat like that? We've already computed this determinant. We found it to be 1/12. And so if I multiply by the adjoint, let's see what I actually generate as a 3 by 3 determinant. I think I'm going to get a 1/4, 0, 1/2. Also a -5/12, is that 2/3? And a -1/2? And finally a 1/12, a -1/3, and a +1/2. It's just a different way of generating the inverse of that coefficient matrix. Well, continuing to cheat, scrolling up a little bit because I'm just repeating myself. Let's come up and see what the inverse of that matrix looked like. Oh, here it is. So I took my glasses off. Does this inverse matrix match up with what I have in green?
Yes. Yeah.
Everywhere?
Yeah, everywhere.
I just had to check, you guys. I wanted to make sure I had no numerical errors along the way.
Okay.
Again, alternative technique, for what it's worth. Well, I guess for me to finish up class today, there is just one last thing I want to mention. A really slick overview of of some results I have not really talked about in class. But, you guys check out the system. The single matrix equation comes from a system of n equations and n unknowns, but it's homogeneous. And so I think no matter what happens, the zero vector is going to necessarily be a solution. It is the only trivial solution to this particular equation. And I maintain the fact that it has a trivial solution simply means when I was able to reduce the matrix A, completely reduce it, I came up with the identity matrix, meaning each and every one of the entries is going to be equal to 0 if the rank is n. Rank just being the number of entries or number of rows of your matrix that are non-zero. So this is a theorem you're going to want to take a peek at. It just simply gives equivalent statements. They all correspond to each other. One can be used to prove the other and vice versa. Dive in there and take a peek at that invertible matrix since I'm finishing up my discussion of matrices and determinants.
This is 2.8.1?
Yeah, it's just the very last theorem you're going to find in chapter 2, the very last one. So, can I ask you guys this big favor? You don't have to necessarily look at the very first section of the next chapter. I'll talk about it. I'll talk about it very lightly because it's just a regurgitation of what you learned back in trigonometry. But I think when it comes to section 3.2, this is where linear algebra truly begins. And I will be in 3.2 heavily. Sorry, I'm so slow. Tomorrow, that's Wednesday. And so if you at all possibly can be caught up, can you just read ahead of me into chapter 4? Start reading carefully that second section, 4.2. Here's where I think you and I are going to be coming into a level of abstraction that is rather significant relative to what you guys have done in the past. Section 4.1, like I said, I'm going to cover very quickly, only because it's just simple trigonometry, nothing more.
So you want us to read 4.2?
Yes.
Okay.
Dramatically. Emphatically, I should
But
say.
4.1,
I'll
just...
cover it. I'll assign
drag
homework
it.
on it tomorrow. It's
Okay.
just going to be so very light, it'll be silly business.
And then 3 we're pretty much done with? Or?
No, I want to assign some homework.
Oh, okay.
Since I have plenty of time.
Okay.
So last night you guys saw systems, right? Using inverse matrix method
Mm-hmm.
and Kramer's rule.
Yep.
So we had homework all the way through 2.6.
Yeah.
Oh, no, we had homework through 3.3.
Well, true. I just meant in
Yeah.
terms of chapter 2, we had homework.
Okay, yeah.
so slow on that.